what's up, you guys? Welcome back to another PY 212 review video. I'm Seven.
I'm Roger.
And I'm Mark.
And we know you've been procrastinating studying for this test, so we're going to give you a Quiz 3 little review session with some practice problems. Let's go!
All right, guys. So now we're going to do an LR circuit problem. So our problem is that we have this circuit that you can see here, and at time equals 0, we're going to switch this flip this switch in order to connect these two nodes, right? So what we want to find is what the initial current is going to be and what's going to be the current after a long time, and then we want to find an equation to describe the value of the current at basically any time. So the first thing we're going to want to do is draw our circuit after the switch is flipped. So we're going to redraw it like this. You can see that those two nodes are now connected up here, and we're leaving this resistor just kind of dangling off into space. So whenever you see something like this where you just have something that isn't connected to anything, you can just ignore it. There's not going to be any current flowing through here because it can't create a loop. So we're actually just going to completely ignore that little dangling resistor. And now this is a very simple loop. And let's think about what is the current going to be through this loop. So initially, at t equals 0, what's going to be the current through this loop? Well, we have an inductor in the loop. And what do inductors not like? They don't like currents that change. So obviously when nothing is connected, there's not going to be any current flowing, right? Immediately when it's connected, the inductor is going to be like, no, I do not like that. So initially, the current through is going to be 0 because there's an inductor in the loop. So the initial current is going to be 0. But what's the current going to be after a long time? Well, inductors don't like changing current, but they can be convinced very slowly over a long time. So as the voltage continues to be applied over the inductor, it's going to get more and more used to what the current wants to be. And then eventually, it's going to be like, all right, you know what, we can have some current. So we're going to get a current through this inductor. And after a really, really long time, what you can do is just treat the inductor as a short circuit. So we can just pretend that the inductor isn't there, and then we just have these two resistors. And we can just pretend that inductor isn't there. So what would the current be through this circuit without an inductor? Well, we know that current is voltage over resistance, and we have these two resistors here. Resistors in series just add up. R plus 3R is 4R. So we're going to get that the current, after a long time, is going to be the battery voltage over the total resistance, which is 4R. Fantastic. But now, what if we want to know the current at some other time than just the initial or just after a very long time? Well, we're going to need some kind of equation to find that out. So our equation is actually very similar to our capacitor equation for voltage, except this time it's for current. So it's going to be equal, well, first we should write IT. This means our current at a given time t. And then that is going to equal our I max, because we always want to have our maximum current, and then some factor relating to time. In this case, we know that it's going to start really low, and then it's going to build up slowly to some maximum I max. And this curve is a curve we've seen before, and we know an equation to describe it. And that equation is 1 minus e to the minus t over tau. And that's it. That's our equation. Psych. What's tau, guys? What's tau? So tau for a capacitor, we know, was R times C. For an inductor, it's very similar. It's actually L over R. But what's the R for our circuit? Well, we got it right here. It's 4R. It's the sum of all the resistors in series. So our tau for this circuit is actually going to be L over 4R. So when we plug that in here, because we're dividing by it, we're going to get, well, first we have to rewrite 1 minus e to the minus t times, we're dividing, so we're just going to flip it, 4R over L. And there you have it. That's the equation for the current at any given time for this circuit. Psych again, we actually have to plug in what I max is. But that's what the current is after a long time. V0 over 4R. So we're actually just going to plug that in. Let me be in the frame. So we're going to get that IT is equal to V0 over 4R times 1 minus e to the minus t over 4R over L. And that's the equation. You can plug in all your values to this, and then for any value of t, you can calculate what the current's going to be. How cool is that? But now, what happens if we now flip the switch back after a really long time? So we remember that after a really long time in the initial, this I was equal to V0 over 4R. And then we're going to flip the switch. It was connected like this, and now we're connecting it like this. And this is our new circuit. Now remember what I said before about having dangling resistors? Well, now this whole branch is not connected to anything. So the battery and the resistor are both dangling, so we just ignore it. We don't care because nothing interesting is going on over there because they're not connected. So now we're just left with this circuit. So what's interesting about this circuit is that we have an inductor that is energized. There is a current flowing through the inductor as the switch is flipped, which means there's still going to be a current flowing through it initially. So our initial current through this circuit is actually going to be V0 over 4R, like it was after a very long time from the previous state of the circuit. But now we want to find an equation for this. So because we have a de-energizing inductor, because it's not being powered anymore, it is just kind of on its own, it's going to be losing energy. So our equation for that is going to be that IT is going to equal the maximum current times e to the minus t over tau. So this is going to decrease in time because we start really high and then we get low over time. So our I max is going to be our max current from before because it's the same current. So that's going to be V0 over 4R. And then what's our tau going to be? Well, tau before was L over 4R, but in this case, we actually have a different circuit because we have 2R here plus R. So our tau here is actually going to be L over 3R because, again, it's a different circuit. There's different resistors. So when we plug that in here, that's going to be minus t, and it's going to be times the reciprocal because we're dividing, 3R over L. And that is the equation after the switch is flipped.
Okay, guys, we're going to be going over problem 1 on the quiz 3 practice problems, which is an Ampere's law problem where we have a thick wire with current flowing through it out of the board, surrounded by a thin cylindrical shell carrying an equal and opposite current. And so what we're going to be looking for is the magnitude and direction of the magnetic field everywhere in this system. And so why is this an Ampere's law problem, right? I said that, but the reason is if we look at our Ampere's law, in general, what stops us from using this effectively is that this integral here, b dot dl, is complicated, and you can't always even write it out and solve it analytically. But just like with Gauss's law, the key is symmetry. And in this system, we can recognize that there's a cylindrical symmetry to our system. So if I imagine my axis pointing along my current, no matter which angle I look at, this way or this way or this way, I see the same thing, right? And so what that means is that the Amperian loops, which I've drawn in this diagram, labeled 1, 2, and 3, you can see they're all circles. And the reason is because of our cylindrical symmetry, the magnitude of B, or anything really, has to be constant along these circular paths, right? And so, right, and that tells us about the magnitude of the magnetic field. And another great thing about this system is that with our circular paths, we actually see that our B vector points along our path, along our DL vector, meaning tangent to our circular paths. And we can see this by either considering a Biot-Savart law approach, where we do an I cross R vector, or we could also, for a current, we can use our right-hand rule where we point our thumb in the direction of current, and then we can see which direction our fingers curl. And you have probably seen that the magnetic field lines around a wire go in a circle, right? And so in these black arrows here, I'm labeling the direction of the magnetic field at certain points along these paths. And so what we get from that is that B vector is parallel to DL vector. Now these two things are what allow us to apply an Ampere's law approach here. So if we consider our left-hand side of the Ampere's law, our line integral, we start with the integral of B dot dl. Since B vector is always parallel to DL vector, this dot product becomes a product of the magnitudes, right? And since the magnitude of B is constant along our paths, we can bring this B vector outside of the integral, like I've done here. And what are we left with? We're left with an integral over a loop of the magnitude of DL vector. And that, by definition, is the total length of our path, right? We're adding up all the small pieces of length along our Amperian paths. And so in each case, that length is going to be the circumference of our circle, which is going to be 2 pi r. And r here is free for us to choose. Specifically, I've drawn 3 Amperian paths here. They're all circles, but the reason there's 3 is there's 3 regions in this problem where the physics is going to be a little different. Right? But this is the case for all of our path 1, 2, and 3. And so if we put this back into our Ampere's law, we can see that our magnitude of B is just going to be mu naught I enclosed over the circumference of our circle. Okay. Now, what's different about paths 1, 2, and 3? Well, it's going to be, the difference is going to be our I enclosed. And so let's start with region 3, our path that I've drawn in black, which is outside both the inner wire and the outer shell. And so the enclosed path, remember, is the current that punches through kind of the whiteboard in this case, the circular area enclosed by our path. And in this case, inside our black circle here, we have 2 currents. We have one current in the inner wire, I, and we have a current pointing in the opposite direction in our outer shell. And so in total, we're going to have 2 currents which are equal in magnitude but opposite in direction. And so our enclosed current is going to be 0 for path 3. Okay, and that's the case for any path I draw outside of both the inner wire and the outer shell. Okay, what about path 2? Path 2 lies between the inner wire and the outer shell. And so that means that I enclosed does not include the current in the outer shell, but it does include this current I here. So I enclosed is I in this case. Okay, now the trickiest one, region 1. And the reason it's the trickiest is because this current flows through a wire with thickness. And that means that this current is distributed along this cross-sectional area inside this blue circle. And it's distributed evenly. Right? That means for any piece of area, of cross-sectional area inside the blue circle, we have the same amount of current. And so specifically, the current that's enclosed in the red circle is proportional to the total current flowing through this inner wire. And the proportionality is the ratio of the area enclosed by the red loop to the area, the total area of this blue circle. And so both those areas are circles, and areas of circles, right? We have pi r squared little r, the same one that characterizes our Amperian loop. That's going to be our red area over pi r1 squared. I didn't label it, but the radius of this blue circle is r1. So that's why I'm using r1 squared on the bottom here. Okay, and you see that we can kind of simplify this a bit. We have pi on the top, pi on the bottom. So I enclosed is r squared over r1 squared times I. Okay, now that we have I enclosed, we can come back to this expression here, which we found by right, using the symmetry properties for our B field. And now we can just substitute in our expression for I enclosed to find the magnitude of B for each radius. Right, so region 3, outside the outer shell, since I enclosed is 0, B is proportional to I enclosed, B is 0. There is no B field outside of the outer shell. Okay, region 2, I enclosed is I, so we just have the magnitude of B is mu naught I over 2 pi r. You might recognize that as the B field from a wire with current I with no thickness, a wire that is just a line. Right? So this is this magnetic field is as if there were no current in the outer shell, right? This region doesn't know about the current here. And it's also as if we took all this current here and we condensed it just to a point here. Right? So that's always useful to try to think about these results. What are they similar to? What do they mean? Okay, and finally, region 1, inside the inner wire. Let's break this into pieces. Let's take our mu naught over 2 pi r, put it out front. And then let's take our I enclosed, substitute it. And we can see that an r cancels with one of our r's here. And we get mu naught r I over 2 pi r1 squared for that magnitude. Okay, and that's our magnitudes of the magnetic field. And the directions, right, because the magnetic field is a vector, like we said earlier from kind of the right-hand rule, our thumb points along current, our fingers curl along B field. So the direction of the B field is counterclockwise, both in region 1 and region 2. In region 3, there's no B field, so there isn't really a direction either. Okay, and finally, I just want to comment on the R dependence of the B field in regions 1 and 2. So region 2, we have something that is familiar. We have a B field that as we get further away, as R increases, the B field decreases. Right? And that kind of makes sense. The further away we are from a wire, the smaller the B field. Okay, What about region 1? Region 1, we're inside a wire. As we get further from the center of our wire, as R increases, B field also increases, right? So that might be a bit unintuitive at first, but the reason is, again, that our I enclosed increases as we get further from the center of the wire. Okay. And what that means is that our B field is actually 0 at the center of our inner wire, and its maximum right at the edge. So if you kind of want to think about those magnitudes a bit, the B field increases, gets to this edge, then it decreases, and then it's 0. So that's problem 1 on the quiz 3 practice for you. Hopefully that was understandable. And remember, Ampere's law, the only reason we were able to do any of it was symmetry, and a good choice of our Amperian loop. So there we go.
Hey guys, it's me again. You hate to see me show up. Anyways, so we're going to be looking at the 8th practice problem on practice exam number 3. All right, let's take a look at what's going on over here, right? So we've got a uniform magnetic field coming out of the page. We've got this little system right here, where this bad boy is a conducting rod, meaning electrons are free to move within it. We have an external force providing a constant velocity going this way on this rod. This rod is free to move wherever. We got wires here connecting to a resistor over here. Cool. That's a setup. I don't think I missed anything else. Oh, the resistance through the wires are 0, but whatever. We assumed that anyway. So first, problem A asks us, what happens when this bad boy isn't moving, right? Well, what does happen when this bad boy isn't moving? Well, if we look at the formula for the EMF of these kinds of systems, we'll notice that V is equal to 0, which means that nothing is happening, right? Nothing is happening. And that matches our intuition, right? Because if this isn't moving, you essentially just have a resistor in a closed loop with nothing powering it, right? So that makes sense, all right? So when V is equal to 0, nothing's going on. No current, no EMF, no nothing. All right, cool. Now part B of this problem is asking us what happens when we actually do start moving this. And remember that there is something that is providing a constant speed for our conducting rod, right? And so part B asks us about the polarity of the system, right? Polarity meaning like, I don't know, is one side positively charged while the other side is negatively charged? What's going on over here, right? And the way that I like to think about this, which I feel like makes the most sense, at least to me, is I like to think about our force on a charged particle due to a magnetic field equation, which is this bad boy right here, right? So if we think about, if we go onto our conducting rod, right, and we think about what happens to just one, like, let's say electron, right? What happens to one electron as it is moving this way, right? If an electron is moving this way, well, we know that this is actually going to be pointing in the other direction because an electron is negatively charged, right? So if we use our right-hand rule for cross products, we'll see that our V vector is going this way, crossed with our B vector, which is pointing out of the page. So then it shows our thumb is pointing in the direction of the force applied on an electron. I forgot to add vector signs over here, but that's fine. So we know that if you're an electron that's moving this way, right, you're experiencing a downwards force due to the magnetic field if you're going this way, right? And so what does that mean? Well, it means that all of the electrons are going to end up building up over here, right? Which means this side of our conducting rod is going to have a net negative charge, right? While this side is going to have a positive charge. Cool, that's all we can say. So we can say that the bottom is negatively charged and the top is positively charged. Cool, sick. Problem C. Now problem C is asking about the current in these, right? And what's happening to the current as this rod is moving at a constant velocity this way, right? Well, if we remember our EMF equation right here, right? This is essentially acting as a circuit. I can redraw the circuit over here to like kind of make an equivalence, right? This is basically a circuit that looks like this, right, with a resistor over here, right? Where this is the resistor R that's over there, same thing, R. But the moving of this conducting rod is essentially acting like a battery, right? It's providing an EMF, right? And so, well, we got our famous V equals IR equation, right? Or we can write it with EMF, I guess, in this case. Oh. Where the EMF is equal to the current times the resistance, right? So we have a resistance R for this resistor over here, right? So we can rewrite this as I is equal to E over R. Whoa, we can write the EMF in terms of the magnetic field, the speed, and the length of the conducting rod right there. Easy money, dude. You got the magnitude. It's just BV L over R. I guess I wrote L in two different ways. It doesn't really matter, yeah. Super, ultra, mega cool. Now let's think about the direction of this current, right? Well, we've already talked about where the electrons are going to be congregating due to the force exerted on them by moving through a magnetic field. So, the negative charges are going this way, positive charges are going this way. Since we're talking about conventional current because it's physics, the current is going to be going counterclockwise. Yeah! Part C. Or is it D? I actually don't remember. Anyways, last part of this problem. There we go. So we're looking at the force exerted by the magnetic field onto the conducting rod over here, right? Well, oh boy, we got an equation just fit for that. Yeah, so first let's look at the direction of which way this force is going to be exerting onto this conducting rod over here, right? So our L vector, it's kind of weird that we're making the length a vector, but like whatever, right? This is just pointing in the direction of the current, right? So if we establish that our current is going counterclockwise, right? We'll point, right hand rule again, who'd have thought? We're going to point our finger in the direction of the current, and then our middle finger in the direction of the B field, which is going to go out of the page, and then our thumb is pointing in the direction of the force exerted on the rod by the magnetic field, which is going this way. Super cool. Hey, Lenz's law, jump scare, you know what I mean? So the force is going to be acting on this way to try and counteract the change in the flux that's going on here, which is pretty rad. It's nice to see it come back, right? So the force is going to be going this way, right? Cool. Now let's talk about the magnitude of the force, right? What's super cool is that since these are perpendicular, we can just multiply the magnitudes together, baby. Let's go. Let's go. You love to see it. And guess what? We just found the current from so this is easy money, guys. This is easy money. So we're just gonna multiply the magnitudes together, where I is gonna be equal to BVL over R times L times B. Oh my gosh, guys. Here's what we get over R. Isn't that just dandy? Phenomenal. That's my time, y'all.